Hello and welcome to another video. In this video we're going to be working on shortest palindrome, and in this you're given a string s and you can convert it to a palindrome by adding characters in front of it. Return the shortest palindrome you can find by performing this transformation. So in this case we can put an a in the front of this guy, and that would be a palindrome. And in this case we have to actually add this whole thing in the front. So this is actually probably the toughest problem I've done on like a problem of the day in a while. So I'm going to explain it, and you basically have to know either KMP or a rolling hash. And so I'll explain the rolling hash, which is what I use. I don't use KMP. But essentially, let's just first figure out like how we would even do this in like a brute force way. So if we have this word AACECAA, just make this bigger. So what would we need to do to like what would we need to do to add 0 characters? So to add 0 characters, and I'm gonna assume you know like basic palindrome stuff, you know, like otherwise I wouldn't even bother this problem. So to add 0 characters, basically this has to be equal to this in reverse, right? So it's not. Okay. So to add 1 character, if we add 1 character, then what has to be equal to what? Well, the original part of the string, this, has to be palindromic, right? So actually, let me add these characters in another color. Actually, hold on. Let's do this, and let's say ACE. Okay. So yeah, so if we want to add just an A, so I'm just going to do separately. If I just want to add an A here, like this, that means this has to be palindromic, and then the character I add can just be like, because I can add whatever I want as long as this section is palindromic, I can just add whatever this character is and that'll be a palindrome. Now if I want to add 2 characters, so another one of these, yeah, let's move this over here, then same kind of thing, right? This has to be palindromic, and so on and so on. So the idea is we can basically take our word and we can figure out, like, starting from the start, what's the longest palindromic sequence we have, and then that will determine how many characters we need to add. So let's say like this is palindromic, then we can just, for these characters, we can just add those over here. And that's kind of the idea. But to determine if something is a palindrome is n squared, best case. Yeah, I think so. Actually, maybe you can actually do it in O of n, but you'd have to do it. Yeah, you'd basically have to do it. Sorry. So it's n squared using most things, but it's O of n using string hashing. Because you have to basically like compare. Actually, sorry. To determine if something is a palindrome is linear. Yeah. To determine if something is a palindrome, like this is linear, right? Because we can just have 2 pointers. And we can just check, like, are these characters the same? If they are, then let's compare these characters, and so on and so on. So that is linear. But if we want to do that again for another one, and another one, and another one, those are all linear. So we're going to have to do that for the whole string. So worst case, that's n squared. And so the way to check if we know, the way to basically, you can get, you can go through a string and turn it in using hashing. You can turn strings into values, and then if you want to determine if a region is palindromic, you can actually do that in O of 1 using string hashing. So first you go through the string, which is O of n, and then if I want to say like, is this palindromic, you can do that in O of 1. So it's kind of like prefix sums, kind of the same idea, where you do some kind of computation, you turn it into hash values, and then you can determine if substrings are palindromic in O of 1. So I'm going to briefly describe how string hashing works. So let's just start with a string, and we're just going to go left to right and kind of explain. So let's say our string is this thing here. So A, C, E, C, A. Okay. So basically the idea of string hashing is we can hash a string to a value, and then we can compare a string to another string in O of 1 time. Because we're basically saying like, this is some value, this is some value, kind of like a prefix sum, right? So imagine all of these are some number, and you're just gonna like add all these up, So imagine it would be kind of the same as, yeah, adding all these up, and then you can query a substring, like what is this equal to in O1. And so the way to do this, the hash function I like to use is you take a prime number. So usually you take this, pretty common. So 10 then plus 7. And you also take a prime number and try to use a bigger one, because basically the idea with hashing, if you use a bad hash function, you're going to get collisions, meaning you're going to get two strings that are not equal, but you'll think they're equal when you compare their values. So I usually use like this as a default. And the other thing you can do is you can have multiple of these that I show you with different prime numbers, and then you could say like you can compare both of those. So I'll kind of explain that maybe a little bit later. But essentially, this is the numbers that I use, and then the value at every single index is the ASCII value at that character. And you can normalize it, so you can do minus ASCII value of A if you want to. That's totally fine, or this is fine as well. Times the prime number that we're using here, so 131, to the index of the character. So an example is like for this character, this E, this would be the ASCII value of E, so whatever that is, whatever number that is, so ASCII E, times 131 to the third. And so that's basically how you convert a letter, and the position of the letter is important, right? Because AACE is not the same as ACEA. So you can't just like take all the ASCII values and add them together or something like that. But basically you can use this to get a prefix hash. So the idea is like this would give you a number, 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 and then you store them like a prefix sum. And every time you get these, you mod them by this number, because these numbers can get really big, as you can imagine. Like imagine the string is like 1,000,000 characters, 131 to the million is going to be some big number. So typically what you do is you do all this modded by your mod value as you keep going. So you make sure that your value stays small. So that will basically give you a hash value of whatever you want. And then if I want like this, for example, this substring, so this is where it gets tricky. So this substring, let's kind of walk through this. Basically, the way it's stored right now is this character is, so I'm going to say A is like the ASCII value for short. And then I'll say 131 to the I. I'll just call that I, just to make that shorter. So basically it's the ASCII value of E times 131 to the third, right? But because this substring, it's first, this should be the ASCII value of E times 131 to the 0. So hopefully that makes sense, basically, because like the power here is going to be like 3, but I want it to be 0. The power here is going to be 4, but I want it to be 1, right? So the substring should be like, this is index 0, index 1, index 2, index 3, and so on. And the idea of how to usually do that is you can't really divide. So if you have an equation like this, let's say I have, well, you know, I'm not even going to have stuff in the front. Let's say I have like x to the 4th plus x cubed plus, or actually it'll be more like this, right? So x to the 0 plus x to the 1 plus x squared plus x cubed, and I want to somehow like get rid of all these x's. Like even if I don't have this, I can't divide because when you do modding, if you do a bunch of modding, you can't divide because your numbers are already like not accurate, basically. So there is a way to do dividing with modding, but it's super complicated. So there's a better way to do it. So if I want something like that, so if I'm trying to convert, you know, x cubed plus x to the 4th plus x to the 5th and so on into x to the 0 plus x to the 1 plus x squared and so on, I can't just take this and divide by x cubed, because you can't really divide after you did a bunch of mod operations. But instead, what you can do is you can get another substring. So let's say this is the value of like my current substring, and I can get another substring with some value, and I can take that substring that's the same length, assuming that started at index 0, and this is correct, right? So that substring is like x to the 0, x to the square, and so on, with this, or x to the 1 plus x squared plus x cubed and so on. And I can take this whole thing and just multiply it by what I need to make it equal to this one. So in this case, I would just multiply it by x cubed, which that would be fine, but you can't divide. So hopefully that makes sense. Kind of complicated. I will also post like the string hashing thing. But so that's basically how you do string hashing. So now let's walk through how we would compare a palindrome in O of 1. So the idea is we're gonna go and we're gonna add characters forward and backwards. So let's just say we have this forward hash, and we're gonna have a backward hash. And this is going to be a little bit different. So remember, forward, it needs to be like x to the 0 plus x to the 1 plus x squared, right? Like if we're adding characters, like if we want AAC, this needs to be to the 0 power, to the 1 power, to the 2 power. But if I want this backwards, and I have, let's say this is my string, right? If I have AA, so it'll be like AA or some x to the 0 plus x to the 1. If I add another character over here, backward, then I'm gonna add x to the 2, and so on and so on. So if I'm adding another character and I'm going this way, that means that as I'm adding more characters, all I have to do is just add like this exponent, because I'm also comparing. The thing that I'm comparing is I'm comparing the forward and the backward, right? So this AAC forward would be like AAC, and backward it would be CAA. And so hopefully that makes sense. So in one of them, it would go forward, one of them would go backward. I think it's actually probably the reverse. So forward, if I want to add characters forward, I would just add x to the x to the whatever power, and then backward, when I add a character, I will have to shift everything else. So I'll kind of explain how that works. Yeah. So let's just walk through how this would work for adding all these characters. So to add this first A going forward, it's going to be the same both because it's just an A. So this will just be and like I say, I'll just say A is short for ASCII value for A, and then this will be times 131 to the 0. So we'll just call this like A0. And then backwards the same thing. So A0. And then we basically check, like, are these equivalent, which they are. And if they are equivalent, then this is a palindrome. So then we know that, like, we can use this as a palindrome, and we can just get the reverse of this to add to the front. Okay, so now let's keep going. So now forward, we want to add another character. So forward, it's actually going to be, the first character is going to stay the same. Now we do A to the 1. Okay, so hopefully that made sense, and now let's take a look at the code. So here we have this 131 that's a power. Oh yeah, and so I forgot to mention, so this is the hash that I used, this is the hash equation that I used, and sometimes you're going to get strings that are not equal, but you'll get them to be the same. So what you can do is you can just take this exact function, and instead of using 131 at another prime number, you can just look up like big prime numbers. And then for equations that are easy, you can use a small number. Instead of 131, you can use like sometimes something even 3 works or something. But basically, I have two different numbers. You know, let's say we have 131 here, and then we have whatever prime number, like 29 or something. And then when you compare them, you compare that these are equal and these are equal. And then if you just make a bunch of hash functions, it's very unlikely that, like, 2 or 3 or 4 are all equal, but the things aren't the same. So yeah, basically have 131. We can actually even try this with 3 and see if it fails, just to see. And yeah, so we have this 10 and then plus 7, pretty common. And then you have the forward hash, reverse hash, and the index of the first palindrome, like, match character. And then we get our letter. And then remember, for our forward hash, what we want to do is we want to add the letter times 131 to whatever power we're at. And so I made like a fast power function. You don't have to do this. Python basically gives this to you for free. But essentially, fast power is like if I want to do something like a base to an exponent modded by something. Yeah, I mean, that's like a LeetCode problem right there. Basically, just like how to do something to a power, right? So if I want to do 131 to the like million, I don't want to just like. So there's 2 ways you could do it. One easy way is you can actually just store them all in a result array. So I could store like 131 to the 0, multiply by 131, get 131 to the 1, multiply by 131, and so on. So you can just cache them in an array. That's one easy way. But if you don't want to do that, if you want to make a fast power function, The idea basically for fast power is you split it in two. So if I have like, 100 to the 1,000 or something, then I can split this in two. I can do like 100 to the 500 times 100 to the 500. And you keep splitting in two, so it's like a logarithmic exponent instead of a linear time. So that's another problem in itself. You can look at that if you want to. Or like I said, just basically make an array of all the values. So you can just loop like for I equals 0 to 1,000. Just store all these, right? So like store 131, 131 squared. And then you can just access those elements for whatever power you. Okay, so hopefully that made sense, and now let's take a look at the code. So here we have this 131 that's a power. Oh yeah, and so I forgot to mention, so this is the hash that I used, this is the hash equation that I used, and sometimes you're going to get strings that are not equal, but you'll get them to be the same. So what you can do is you can just take this exact function, and instead of using 131 at another prime number, you can just look up like big prime numbers. And then for equations that are easy, you can use a small number. Instead of 131, you can use like sometimes something even 3 works or something. But basically, you have two different numbers. Let's say we have 131 here, and then we have whatever prime number, like 29 or something. And then when you compare them, you compare that these are equal and these are equal. And then if you just make a bunch of hash functions, it's very unlikely that 2 or 3 or 4 are all equal, but the things aren't the same. So yeah, basically have 131. We can actually even try this with 3 and see if it fails, just to see. And yeah, so we have this 10 and then to 7, pretty common. And then you have the forward hash, reverse hash, and the index of the first palindrome match character. And then we get our letter. And then remember, for our forward hash, what we want to do is we want to add the letter times 131 to whatever power we're at. And so I made a fast power function. You don't have to do this. Python basically gives this to you for free. But essentially, fast power is if I want to do something like a base to an exponent modded by something. Yeah, I mean, that's like a LeetCode problem right there. Basically, just how to do something to a power, right? So if I want to do 131 to the million, I don't want to just so there's 2 ways you could do it. One easy way is you can actually just store them all in a result array. So I could store 131 to the 0, multiply by 131, get 131 to the 1, multiply by 131, and so on. So you can just cache them in an array. That's one easy way. But if you don't want to do that, if you want to make a fast power function, the idea basically for fast power is you split it in two. So if I have 100 to the 1,000 or something, then I can split this in two. I can do 100 to the 500 times 100 to the 500. And you keep splitting in two, so it's a logarithmic exponent instead of a linear time. So that's another problem in itself. You can look at that if you want to. Or like I said, just basically make an array of all the values. So you can just loop for I equals 0 to 1,000. Just store all these, right? So store 131, 131 squared. And then you can just access those elements for whatever power you want. So that's basically that. And then you keep modding at every step because you want to keep it for Java. You're going to get overflow really fast. So you want to keep modding. And then reverse hash, remember, is you take the old reverse hash value, you multiply by power, basically take the old hash value, multiply by x to get everything to a bigger power, and just add the current ASCII value because that will be multiplied by power to the 0. Then if they're the same, mark the location as this is a palindrome. And then we basically just get the suffix and reverse whatever we need. So, if this is a palindrome, we just get whatever's left and just add the reverse to the front. And we want the biggest palindrome possible because that's going to be the best result. And yeah, so this mod power is a fast power. Yeah. And so I would recommend learning this if you want to. So I think this is actually the problem with our 3. So you see, we have we thought this was a palindrome, I think, and it's not because our exponent is small. So we could try 7, see if that works. So you don't really usually need 131. Yeah, so as the problems get harder, they're going to make it so you have false positives more often. But basically, the bigger number, the more likely it is for you to not have false positives. So something to think about. Yeah. So actually, ideally, I think for powers, you'd probably actually want to store them in an array instead of using this fast power, because the fast power you're going to access a bunch of different times. So I think it's actually inefficient. So I think you would actually just either store your powers in an array or just calculate them on the fly. So if I have like 131 to the 10th and I want 131 to the 11th, I could just multiply by 131 again. I think that's probably better. So instead of using this, just maintain a power and then at every iteration, just multiply it again by whatever it was. I think that's actually going to give you a better result than this, to be honest. So we'll just say we did that for simplicity and for time complexity. So basically, if we did do that, then rolling hash is linear. And then, yeah, this would basically be constant because we're just taking our old power and multiplying by, by whatever. Like if we have 131 to the 5th, we just multiply by 131 again. So you could store like your power in the forward direction and your power in the backward direction, even though I think they're the same. The number you need to store is basically just 131 to the I is what you need to store. So you can do that as well. In fact, we can even do that if we wanted to. So we could say like, let's see. So we could do this, I think. We could do pow here. And then this is, so we definitely want to have another thing. So we want to have pow, or we want to have like, or cur pow or something. I don't know. Or whatever, or like prime. This is fine too. So we'll make this 1. Okay, so this is pow, and this is prime. And then just at the very end, we could just say pow. I guess probably want like lowercase. So you could say like pow equals pow times prime. And we can mod it. I think that actually would work better. Let me get rid of that. I think. Yeah. So I think this will be faster actually. Okay, so I think this is the problem. This thing can get really big, so let's just use that. I think this is fine because it's never going to change. Yeah, let's try that. Okay, so now you can see it's faster because we're basically calculating power in O1 for sure. So this is O1, 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 everything's O1 now. So O1, space. I guess we did make a suffix, but you can do it in O1 if you want to, N1, whatever. You can do a rolling hash in O1 if you just calculate the hash as you go and the power as you go. If you do need a chunk, like if you need to get substrings a bunch of times, then you do need to store a prefix sum. But same kind of thing, you know, for some prefix sums you can just calculate on the fly because you don't actually need to query this a bunch. You just need the current biggest thing that as I'm going. So yeah, if you do need to query this thing, then you need a prefix sum or a array of hashes at each index. Otherwise, you can do it in constant time. Same thing for the power. So yeah. But yeah, I think that's gonna be it. Definitely a harder algorithm, kind of annoying to code for sure. Easy to make mistakes. So you can do like, there's like a needle in a haystack easy problem. You can basically solve it using this thing. You can try it if you want some practice with it. It's pretty rare, so like I think I've seen it at a bunch of LeetCode contests in a row is why I learned it. And yeah, you only need to learn, if you do want to learn some kind of good string comparison function, either learn this or KMP, whatever you prefer. But the nice thing about this is you can use it to compare like arrays, dictionaries, other stuff. Has a lot of uses, I think. And you learn just like how hashing works and stuff, so kind of cool. But yeah, that's going to be all for this one. Hopefully you liked it. If you did, please like the video and subscribe to the channel, and I'll see you in the next one. Thanks for watching.